This research paper explores approval-based committee voting under uncertainty, where voters express uncertain approval preferences over candidates. The study considers 4 uncertain approval preference models: joint probability, lottery, candidate probability, and a restricted version of the latter. The authors investigate problems that take into account uncertain approval preferences to compute desirable committees that satisfy representation with high probability, focusing on justified representation, junior, and stronger proportional representation axioms such as PJR and EJR. A detailed computational complexity analysis is undertaken for several problems, including JR probability, is POS JR, is NEC JR, exists NEC JR, and max JR, with a central focus on justified representation. The results show that exists NEC JR is NP complete for all models, while is POS JR is computationally hard for the lottery model and polynomial time solvable for the other models. These results are summarized in Table 1. The study builds upon previous work on approval-based committee voting under uncertainty and query complexity, as well as similar models in allocation and matching problems. The authors introduce 3 uncertain preference models, where voters have uncertain approval profiles with given probabilities, probability distributions over approval sets, or approve each candidate independently with a given probability. The paper's results highlight the computational complexity of problems such as checking whether a given committee is possibly or necessarily junior, PJR, or EJR, as well as computing the committee that maximizes the probability of satisfying these axioms. The authors show that these problems are NP-complete or CONP-complete, depending on the uncertainty model and the specific problem considered. The study contributes to the understanding of fairness and representation in collective decision-making under uncertainty, providing a comprehensive analysis of uncertain approval preferences in approval-based committee voting. In the context of approval-based committee voting under uncertainty, various models have been proposed to capture voters' preferences, including the 3-valued approval, 3VA, model, the joint probability model, and the lottery model. The 3VA model, applied to ABC voting, specifies a subset of approved candidates, a subset of disapproved candidates, and the remaining candidates are considered uncertain with equal probability. The paper explores the concept of approval-based committee voting under uncertainty, focusing on the justified representation, junior, criterion. It proves that the problem of deciding whether a given committee W satisfies the junior criterion with probability 1 is solvable in polynomial time for the lottery model. This is achieved by defining a set V of voters who are not represented in W under at least one of their plausible approval sets and checking whether any candidate C in C, W is approved by at least K or more voters in V. If this condition is met, then W does not satisfy junior with probability 1. The paper also shows that the necessary junior problem, which is deciding whether a given committee W satisfies junior with probability 1, is solvable in polynomial time for the joint probability model, 3VA model, candidate probability model, and lottery model. Furthermore, the exists necessary junior problem, which is deciding whether there exists a committee W that satisfies junior with probability 1, is shown to be NP-complete for the 4 models by reducing from the NP-complete problem of size JR. This result highlights the computational complexity of deciding whether a committee satisfies junior with probability 1 in the context of approval-based committee voting. 2 lemmas provide further insights into the necessary junior problem. Lemma 1 shows that the size JR problem is NP-complete by reducing from the NP-complete problem of candidate cover. Lemma 2 shows that a committee W satisfies junior with probability 1 if and only if W equals C and K equals C, under the candidate probability model. Finally, the paper concludes that the exists necessary junior problem is NP-complete for the candidate probability model by reducing from the NP-complete problem of size JR. This result underscores the computational complexity of deciding whether a committee satisfies junior with probability 1 in the context of approval-based committee voting. The problem of deciding whether a committee satisfies the justified representation, junior, property with probability 1, denoted as exists NEC JR, is shown to be NP-complete for various voting models, including the 3VA models, lottery model, and joint probability model. This is proven through a reduction from the size JR problem, which is known to be NP-complete, by constructing a new instance I, from an instance I of size JR, where the number of voters and candidates is doubled, and the approval profiles are modified to ensure that the junior property is satisfied with probability 1. The reduction can be done in polynomial time, and it is shown that every yes instance of I is a yes instance of I, and vice versa, implying that exists nec JR is NP-complete for the aforementioned voting models. Furthermore, exists nec JR remains NP-complete even when minimal uncertainty is present, specifically when there are only 2 approval profiles associated with a positive probability. However, it is proven that exists nec JR is in P for the lottery model when each voter approves of only one candidate in each plausible approval profile, which can be solved by counting the number of voters who potentially approve each candidate and selecting the candidates with a count greater than or equal to n, k. The JR probability problem, which determines the probability that a given committee W satisfies the joint responsibility, junior, property, is also explored. It is shown that JR probability is in P for the joint probability model, but N-FARD for the lottery model, and P-complete for the 3VA model. The P-completeness is proven through a reduction from vertex covers, the problem of counting the number of vertex covers for a given graph, which is P-complete. Additionally, JR probability is in P for the 3VA model if the approval probabilities are binary, and counting the plausible approval profiles where W satisfies junior can be computed in polynomial time if k equals n. The research paper delves into the complexity of approval-based committee voting under uncertainty, focusing on the concept of justified representation, junior, and its stronger notions, extended justified representation, EJR, and proportional justified representation, PJR. A novel formula for computing plausible approval profiles is introduced, which can be calculated in polynomial time, leading to the discovery that max JR is N-FARD for all 4 uncertainty models considered. The authors then turn their attention to EJR and PJR, providing answers to the computational problems under these concepts. They prove that ISNEC EJR and ISNEC PJR, the problems of deciding whether a given committee satisfies EJR or PJR with probability 1, are both CONP-complete for all 4 uncertainty models. Additionally, they demonstrate that exists nec EJR and exists nec PJR, the problems of deciding whether there exists a committee that satisfies EJR or PJR with probability 1, are con-FARD for the candidate probability and 3VA models. The authors also show that max EJR and max PJR, the problems of computing a committee with the highest probability of satisfying EJR or PJR, are con-FARD for all 4 uncertainty models. This follows from the CONP hardness of exists nec EJR and exists nec PJR. The paper concludes by suggesting future directions, including exploring other axiomatic properties, developing approximation or fixed parameter tractable, FPT, algorithms for the max JR problem, and examining restricted versions of approval preferences. The research acknowledges the support of various grants and funding schemes and provides a comprehensive list of references. The paper employs technical terms and notation from the field of artificial intelligence and computer science, including complexity theory and algorithm design, and is intended for an expert audience.